Okay, I've got a number of questions regarding the homework, and so I'm going to do out a few examples. So if you are able to do the homework, no problem. If not, hopefully these will help you follow along. So first of all, here I've just simply written out the first line of the periodic table. You don't have to do this. I'm just simply trying to remove some of this clutter that's there. I've just taken this line here, so the lithium, beryllium, boron, etc. This line here, I've written it out like so. You have your chemical symbols here, the small number on top, which is my atomic number, which is my number of protons, and I also have the larger number, the mass number. Now that's in pencil because we're not going to be really using those figures today. So one of the key things, even though the atomic number tells us the number of protons, it also tells us the number of electrons. So here we have what I have drawn is we've started to draw the nucleus and the orbitals or electrons around each of these atoms. So I've already drawn the first two electrons in each one. In this case, this is lithium. So lithium has 3 protons, and it also then has 3 electrons. I've drawn 2 electrons, so I still need a 3rd electron for my lithium. So I'm going to draw that here. So now my lithium has 3 electrons. I have drawn my lithium completely. Next we have beryllium. Again, I have already previously drawn my 2 electrons. So it has a total of 4 protons and a total of 4 electrons. So I have here, I'm going to add in my next 2. So now I have 1, 2, 3, 4. 4 electrons for beryllium. Now we have boron, and you probably are starting to see a trend here. 1, 2, 3, 4. And let's put in 5 there. Again, for carbon, I have 6. So 1, 2, 3, 4, 5, and 6. For nitrogen, I have 7. So 1, 2, 3, 4, 5, 6, 7. Oxygen has 8. So 1, 2, 3, 4, 5, 6, 7, 8. And fluorine has 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Apologies, I filled those in slightly incorrectly. I should have done the same ordering as before, but I still have the 9 electrons around it. And then finally my neon with 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now I have drawn what's called the Bohr diagrams for each of these atoms. Now, the key thing here is the octet rule. So oct, meaning 8. You can think of it as an octopus. So that's why an octopus has 8 arms. And so atoms are stable, or they're happy, when they have 8 electrons in their outer shell. So think about it, an octopus is happy when it has 8 arms. The other key point, we'll come back to that last little point there, is that an atom can gain or lose electrons to become stable, i.e. to get 8 electrons. There is an exception, which is this one, so that if there is just 2 electrons in the first shell, so that's why I had drawn these ones first, then it can also be stable. So let's look at our lithium. It currently has just 1 electron, drawn in the blue, around in its outer shell. It doesn't have 8 electrons in its outer shell, therefore it's not happy. Likewise, beryllium has 2 electrons in its outer shell, but it's not agreeing with this because if it has 2 electrons in its first shell, it already has a first shell with 2 electrons in it, and therefore it is unhappy as well. And so on with all of these electrons, whereby in its outer shell, so we can put a one here, electrons in outer shell. Here we have 1 electron in its outer shell, 2 electrons in its outer shell. Here we have 3, 4, 5, 6, 7, and 8. And as you can see here for our neon, it has 8 electrons in its outer shell. Therefore, it is stable and happy. And so this is the ideal configuration that atoms want to achieve. So the task for the homework was kind of looking and seeing which atoms can pair up so that, for example, lithium might lose its 1 electron and give it to fluorine, whereby lithium has 1 electron. If it lost that 1 electron, it would have just 2 electrons in its first shell, so ticking that box here, and therefore be stable and happy. That lost electron could go to fluorine, and suddenly it had, which had 7 electrons in its outer shell, now has 8 electrons in its outer shell, and therefore becomes stable and happy. I'll do one of the questions now. Okay, so here we have our first question for homework. How many atoms of lithium are needed to combine with 1 atom of chlorine? So looking at my table here, I have my lithium, and I can see that it has 1 electron in its outer shell. But chlorine isn't in the second period of the periodic table. Looking at my periodic table of elements, I can see that my chlorine is here. It's underneath fluorine. So what that tells me is it's in the same group. And so it means that it has the same number of electrons in its outer shell as fluorine. So here I can look at fluorine and I can see that it has 7 electrons in total, but it 7 electrons in its outer shell with 2 on its inside. So what that means then is that if I look back to here with my diagram here, how many atoms of lithium are needed to combine with 1 atom of chlorine? My lithium has 1 electron in its outer shell, as it's in group 1. So I can draw that. So I can say, then I have my chlorine is in group 7, like fluorine, and so it's going to have 7 electrons in its outer shell. So we have 1, 2, 3, 4, 5, 6, 7. And I can test that's right, so whereby here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17. And then here I have my chlorine. Yes, chlorine has 17 electrons. But what's key is that this has 1 electron in outer shell, and here we have 7 electrons in its outer shell. So again, we're trying to follow the octet rule, so whereby we need 8 electrons in its outer shell, or 2. And here with my lithium, so let's just, this is my lithium, this is my chlorine. It's going to require an awful lot of effort for me to try and put 7 more electrons onto my lithium to get a stable outer shell of 8. So it's easier for me just simply to remove this atom from lithium and give it to chlorine. Therefore, my lithium will have 2 electrons in its outer shell, and chlorine will have 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. So how many atoms of lithium are needed to combine with 1 atom of chlorine? The answer, it's 1 lithium atom. And we can write that chemically as LiCl. Okay, I'm going to do question C because this is again in the same format as the question A, whereby we were asked how many atoms of potassium are needed to combine with one atom of sulfur. So this time with my potassium, so K is the symbol for potassium and S is the symbol for sulfur. Potassium and sulfur are not in my first line, or rather the second period of the periodic table. This is my first period, second period. Third period, I find my sulfur, it's underneath oxygen, and I can see here that my potassium is in group 1 underneath the lithium. So all the groups have the same number of electrons in their outer shell. So potassium is just like lithium, it has 1 electron in its outer shell. Sulfur is like oxygen, which we learnt up here, has 6 electrons in its outer shell. So again, I can just draw my 1, 2, 3, 4, 5, and 6. So here I have my potassium. It has 1 electron. It's easier for me to lose that 1 electron than to try and put 7 electrons onto it. Likewise, my sulfur is trying to get 8 electrons on its outer shell, and it has 6 electrons. So what I try and do is that I take 1 electron and I give it to my sulfur. It's going to go in there. But I don't now have, so well, my potassium is now stable. Got 8 electrons in this outer shell. My sulfur is still not happy. It still is missing an electron. And so we need to have a second potassium. And rather than draw all those diagram here, I'm just going to draw the outer shell with 1, and it's going to give it here. So I need 2 potassiums in order to stabilize my sulfur. So again, we put our metal first, which is our K, followed by our non-metal, which is our S. I know it's 2 potassiums, so I write it just like H2O. I need to have a K2S, and that's a subscript to a small 2 on the bottom. So that's my chemical compound. And the answer to the question though was how many atoms of potassium. So I need 2 atoms of potassium. And that would be the salt or the compound that is formed. Okay, finally, we have the other 2 questions, which is what is the formula of sodium iodide and what is the formula of calcium oxide. I'm going to just change this slightly just to make it easier for the description of whereby I'm changing it to lithium fluoride and beryllium oxide, in the sense that these are all then the elements on this line here of this. But as we learned from the last one, all of the other elements down the group behave the same. So in the sense that the potassium was K, had 1 electron on its outer shell, and so is very similar to how lithium is. Likewise, sodium is also in the same group, and so also behaves like my lithium as here. So what we do is, so this is the bit where, we might remember from class where I was talking about valency. So this is where we kind of write what the outer electrons is of the shell, where we start with our 1, 2, 3, 4, and then we start to count backwards. So we go 3, 2, 1, and ending with 0 here on our noble gases. So what does that valency mean? It basically is just a kind of a fancy way of writing which is the easiest way to get to stability. So here, the valency is 1 because I can lose 1 electron and get a stable shell. the valency of here is 2, whereby I can lose 2 electrons and get a stable shell. Here I can lose 3 electrons and get a stable shell. 4, it doesn't matter either way. I can either gain 4 electrons or I can lose 4 electrons in order to get my stable shell. Here, when I have 5 electrons in this in the outer shell, it's easier for me to gain 3 electrons to get to 8 than it is to lose the 5 electrons, and therefore my valency is a value of 3. Likewise, for 6, I can easily gain 2 electrons for my 6 to become 8, to become stable, and likewise for 7, whereby 7 plus 1 gives me my 8. And then this is why I have a valency of 0 for my noble gases, is that I don't do anything with my noble gases. They already are stable, being 8. So now that I have my valency numbers, I can now go and look and see what is it that the elements in question. So my lithium, so my number of electrons in the outer shell, my lithium has 1 electron inside a shell, and my fluorine has 7 electrons in its outer shell. And we'll do this one as well. So my beryllium has 2 electrons in its outer shell, and my oxide has 6. From this, we now can work out the valency, or as I said, if we used our periodic table, we could have just drawn those numbers on the top and carried it down directly. So you didn't have to write that line, I'm just kind of showing it there so it's a little bit clearer of where these things are happening. So my valency is 1 for my lithium, because I just am wanting to lose that 1 electron. And my valency for my fluorine is also as 1, whereby I'm trying to gain 1 electron. So that's why it's a valency of 1 to 1. And likewise, my beryllium is 2. So I'm trying to have my 2. I have 2 electrons in the outer shell. It's easy for me just simply to lose those 2. So I now have that as a 2. And then my oxygen here has 6 electrons in the outer shell. It's easy for me to gain 2 electrons here. So again, I have my 2. And now that I see my valency, I can see this is a 1 is to 1, and this is a 2 is to 2. So in the sense that this one is wanting to lose an electron, this is wanting to gain an electron. So we have a perfect match. And so I can just simply say this is lithium fluoride. So just as in algebra, whereby there's a kind of, you can imagine an invisible 1 underneath both of those. And likewise with the beryllium and the oxide, each one is wanting, the beryllium is trying to lose 2 electrons and the oxygen is trying to gain 2 electrons. And so therefore it is BeO. So there are my 2 formulas for this. I should have said, sorry, of course, here, the "-ide" on both of these means that only the 2 stated compounds are the only chemicals in it. If it had ATE, it would mean that there was also some oxygen involved in the mix. But "-ide", it's only the sodium and the iodine, or in this case, the lithium and the fluorine. If we were to say to have it that, let's choose another way of doing this. So we haven't done, let's choose the lithium again, but this time we're wanting to combine it with nitrogen. So here I have 1 electron in outer shell, and my nitrogen has 5 electrons in its outer shell with a valency of 3. So I now have my valency of 1 and 3. I no longer can do a 1-to-1 ratio. I need to have 3 lithium instead of for each one of my nitrogen, because each lithium is only providing 1 electron. So therefore, one way in which, so then it's my lithium 3 and nitrogen. And one way you can think of that is we have this kind of crossing over, putting it that way. Though, as I said, remember we don't write that 1, so we would need to just tidy up our answer there to make that lithium I hope that makes it a little bit clearer, and best of luck with trying to work out the other questions.